If you have ever stared at the DSC curve and wondered, okay, I see these peaks, but what do they actually mean for my material? This video is for you. In the next slides, I'm going to show you exactly how to read a DSC curve, what the glass transition, the cold crystallization, and melting peak tell you. Most importantly, how this connects to real material behavior. I'm Mo, a PhD in polymer science. I've been using DSC since my university days and now apply it daily as a product development specialist. Let us get into it. Differential Scanning Calorimetry, DSC, measures heat flow into or out of a material as you change the temperature. You have two pans, one with your samples, one empty as a reference. Both are heated at the same rate, for example, 10 degrees C per minute. The instrument measures the difference in heat required to keep both pans at the same temperature. When your sample undergoes a thermal event, melting, crystallization, glass transition, it either absorbs or releases heat. The difference is what you see as a peak or a step on that curve. You can see here we have peak for cold crystallization for the melting and a step for glass transition temperature. One key thing to understand right away, DSC measure enthalpy change. This is what connects the curve to your material structure. Here, for example, here in this graph here, the y-axis is a heat flow, typically in milliwatts or watts per gram. The x-axis can be temperature or time, and in different software, it can be changed, the exo or endo, the way that the software is showing. For example, here the exo is up, the endo is down, and you see the glass transition temperature, the cold crystallization temperature, and the melting peak. Okay, let's start with the glass transition temperature. The glass transition temperature, TG, is not a peak. It's a step change in heat flow. We can see here we have a step change. This is where your polymer goes from a glassy, rigid state to a rubbery mobile state. At TG, the polymer chains gain enough energy to move. You will see a baseline shift. We can see here a shift from up to bottom, a small step. The midpoint of that step is your TG. For example, for PLA, which I worked with extensively, TG is around 55 to 60 degrees C. Below that, the PLA is stiff and brittle. Above it, the chains start to move. Why does this matter practically? If your packaging material has a TG of 55 degree and it sits in a car in summer at 70 degrees, it will soften. This is design problem. Let's go to the cold crystallization temperature. After TG, if your polymer can crystallize, you will often see an exothermic peak. Heat is released as chains organize into a crystalline structure. This is called cold crystallization because it happened on heating above TG here. For example, in PLA, this peak typically appear around 100 to 120 degrees. The area under this peak, the enthalpy of cold crystallization, tells you how much of material crystallized during the scan here on the chart. Let's move to the melting peak. Then comes the melting peak, endothermic. Heat is absorbed. For PLA, TM is typically around 165 to 175 degrees Celsius. The area under the melting peak gives you the enthalpy of melting. You can use this to calculate the degree of crystallinity of your sample, a key parameter for mechanical and barrier properties in packaging. Let me show you the actual calculation for crystallinity. This is what you will use in your papers and reports. The formula here is degree of crystallinity equals the melting enthalpy minus the cold crystallization enthalpy divided by the theoretical melting enthalpy of 100% crystalline sample that you can find in the literature times 100%. For example, for the PLA, the reference value for a fully crystalline sample is 93.7 joules per gram. So if your DSC shows a melting enthalpy of 40 joule per gram and cold crystallization enthalpy of 25 joule per gram, your crystallinity is 40 minus 25 divided by 93.7 times 100, which gives you about 16%. Why subtract cold crystallization? Because that crystallinity formed during the DSC scan itself, it doesn't in your original sample. This number is very important because higher crystallinity means better barrier properties, better thermal stability, but usually lower impact strength. For packaging, you always balancing these. Now let me tell you the mistakes I see most often. Mistake number 1 here. Not checking the thermal history of your sample. If someone processed the polymer at a high temperature before you, the crystallinity in your DSC curve reflects the history, not the virgin material. Always do a first hit, cool at a control rate, then do the second hit for a normalized result. Mistake number 2, we can see here, using the wrong reference enthalpy value. If your sample is a blend, say PLA with PBAT, you cannot use PLA's reference enthalpy directly. You must weight it by the mass fraction of PLA in the blend. Mistake number 3, ignoring the heating rate. Standard is 10 degrees per minute. If you change the rate, your TG, TC, and TM will shift. Always report your heating rate in your methodology. And the last one, sample mass matter. Too little, the signal is noisy, too much, and you get thermal gradient. And the ideal range is 5 to 15 milligrams for most polymers. Okay, let me show you a real example from my research. In my PhD, I was working on PLA PBAT blend non-composite reinforced with cellulose nanocrystals. DSC was critical for understanding how CNC addition reflects crystallization behavior. We found that CNC acts as a nucleating agent. It increased the crystallinity rate of PLA. You can see here we have a shift in crystallization, cold crystallization peak, and shifted the cold crystallization peak to lower temperature. This showed up clearly in the DSC curves and correlate directly with the mechanical improvement and that we measured. This is the power of DSC. It's not just a measurement, it explains what your material behave the way it does. If this video helped you, subscribe. I publish new videos on polymer, characterization, and packaging, flexible packaging every week. If you have a question about reading your own DSC data, drop it in the comments. I read every single one. See you in the next one.